And my intention is to do a variety of relatively straightforward questions to show you how we implement conservation of energy questions. More importantly, how they are likely to be implemented on the AP exam. The problems we're going to do first today are going to be largely mathematical, and I intend to show you variations to them so you can see how they will change the problems from time to time. This one is probably as easy a problem as I can put together. So we're going to start with a 2 kilogram box that has a current velocity of 5 meters per second along a frictionless surface. Now, there's a number of questions that could be asked here. Probably the easiest question, or the most likely starting question, would be, what is the maximum height attained by the box? Does everybody recognize that the box is going to be hurled into the air? Okay. So assuming the box goes straight up after it's been tilted by that ramp that's there, we want to find out the maximum height attained by the box. Now, in order to do any conservation of energy question, you're going to be attempting to compare one state of the problem with other states of the problem. This is how conservation of energy questions work. In general, conservation of energy questions are less about energy and more about asking questions about velocity, height, or displacement. That generally is what these questions are about. They can all be solved with force problems, all of them. Generally, they can also all be solved with motion equation problems. This is another way of dealing with the information you're given. Going through force tends to take a long time, but will get you to an answer. Going through motion equations tends to also be laborious and requires that you have a whole bunch of things memorized. Here, although you still have things you have to memorize, it's a little bit easier. It's the same stuff over and over again. The first thing you have to be able to do in many of these problems, though, is contextualize what's happening. Can you imagine that over time, the box is eventually going to make it to a position like here, where it will come to rest above the table? Does that make sense? Because if that doesn't make sense, none of this will make sense to you. All right. Well, if that does make sense, then I notice that there are two states of the problem. The state when the box is on the table, moving at 5 meters per second, and the state when the box has made it to its maximum height. At each state, there is the possibility of 3 forms of energy. Now, in these problems, it's probably best that you start the problem by identifying what you're going to call the reference level. Remember, with gravitational potential energy, there has to be reference. What are you measuring the height from? I think this one has an obvious reference level in that I'm going to set the ground or the table here to be our reference level. Does that make good sense to you? So then you go through this list. Is the object pressed up against a spring or a piece of elastic? If not, there's no elastic potential energy. Is the object above the reference level? No. So there's no gravitational potential energy. Is the object moving? Here so. So there is kinetic energy. Looks like to me at state 1, there's only kinetic energy. All right. State 2, is the object pressed up against a spring? Is the object above the reference level? So we've got this one, not this one. Is the object moving? We want the maximum height. That's got to be when all the energy has been converted to potential and there's no kinetic. If it had kinetic, that means it's moving either up or down. So we're going to assume maximum height is when there's no kinetic. All right, so state 2, all I have is gravitational potential. Now, this is one of those statements that I say and you guys don't think about after I say it. You should think about it, because this is like question D or C on or E, at the end of an FRQ when you're already tired and confused. And I say, well, I tell you that in class, but you guys don't ever hear it. These are only equal if something doesn't take energy out of the system. You should always make sure you ask yourself if there's something there that took energy out of the system or something there that added energy to the system. Either one of these makes these not equal. So these are only equal if the system is closed and nothing is applying a force to the system, something external. So if there's no friction, nothing bled energy out of the system, and there's no secret thing pushing on the object to make it go faster, there's nothing adding energy to the system. But ask that question, because I'm definitely going to. But at this point, the problem is pretty easy. 1/2 mv squared, kinetic energy, equals mgh. That's it. And here's why I say, do you need to do the math on that? Because I certainly don't. But if you want to do the math on it, you should. I just don't see any real reason to do the math on this. So try it. Find out what the height is. Get an idea. Make sure you can do the math. But just be aware, this is not where the problem ends. All right. So 25 squared divided by 20, right? So, I'm sorry, just 25 divided by 20. Not particularly hard, I hope. So, any trouble with that? You got your 1 point whatever meters. What if I'm interested in a different case? Like maybe it's still on the ramp and it's moving at 3 meters per second. How high is it off the ground now? Like, still moving, so it hasn't made it to the maximum height. How high is it when it's still moving 3 meters per second? I don't have to change what happened when we talked about object at state one. State one isn't any different. Just asking a different question now. At state three, are we pressed up against a spring? Are we above the reference level? Are we moving? All right, that's it. So I have state three now. State three has gravitational potential energy and kinetic energy. If nothing took energy out of the system, this also must be equal to the other states. There's not a whole lot here to do different, except that now, instead of comparing it to state two, I'm going to compare it to state three. I'm going to have mgh plus 1/2 mv squared. Not much different, but a little different. Now, I don't want to do the math on this. You guys can do the math on this on your own time, I think. Do you need me to do the math on this? You should be honest, because I am bored by doing math. I will state that, do we know whether the box is going up or going down? Do you realize the answer would be the same if this box was on the way up or if it was on the way down? That there wouldn't be any different. There's no way to tell whether the velocity was up the ramp or down the ramp, because I square the velocity. It ends up being the same. So it reaches this point on the way back down too. Same place. Unless something takes energy out of the system. Keep going. These are easy or hard? I'm going to make them harder. All right. Your silence means quiz time tomorrow, that there should be no difficulties tomorrow. And they're always easy when Mr. Shelton's working on them. Always. So let's make this one, I don't know, same level of difficulty, I guess. These feel all the same to me. But you guys tend to feel differently about that. So I'm going to have this situation. All right, so I've got a table that's a really tall table, but okay. And a box here on the top of this ramp that's 0.5 meters above the table. And I'd like to know how fast the box is going just as it leaves the table. And let's stick with our theme. Make the table and the ramp frictionless. Conservation of energy question. Not a whole lot here, but a little different from the last one. I'm going to release the box from rest on the ramp. And I'd like to know how fast it's going just as it leaves the table. So, do you notice that there are two states of the problem? I notice two states of the problem. Now, I'm intentionally putting this problem in front of you to see if I can't trip you up, and I'm going to trip some of you up. You should have a question. If you don't, you didn't pay attention yesterday. And I'm going to talk right over Kyle so he doesn't get to ask this question, because I want to make sure everybody's seeing what it is that I'm asking. Let's start by talking about state one. Is the object pressed up against a spring? No. Is the object above the reference level? All right. What's the reference level? How many of you think it's a table? How many of you think it's the floor? All right. It doesn't matter. If you want to make it the table, make it the table. If you want to make it the floor, make it the floor. Tell you what I'm going to do. I'm going to write out what it would look like for each. That way, there's no confusion. It will not affect the answer. I know that it has no kinetic energy. It's being released at the top of the ramp. It's state two. So I'm going to put table here for that being the reference, and floor. So for the floor, still has gravitational potential energy if the floor is the reference level. Now, at state two, is the object above the reference level? It depends. If you said the table was the reference level, it has no gravitational potential. It's on the reference level. If you said the floor was the reference level, then yeah, it's still above the floor. It has gravitational potential energy. Is it pressed up against a spring? Still no springs. Is it moving? A lot of people nodding here, which means you're letting Mr. Shelton do all the work. But is the box moving at state two? I think so. If they're asking you how fast it's going, you probably should assume it's moving at state two. They want V, and that's only going to be in the kinetic energy. Now, whether you did this problem with the table being the reference level or you did this problem with the ground being the reference level, it's still going to work out to give us the same answer. It has to. Physics can't change just because you picked a different reference level. The reference level is arbitrary. So I'm going to have M, G, H for the people who picked the table as the reference level. The H is 0.5. And I'm going to have M, G, h, where h is 2 if you pick the ground to be the reference level. Now that has to be equal to state 2, assuming nothing took energy out of the system. Put that question mark in there just to make sure you're asking yourself. In this case, it's frictionless, so I'm thinking no, nothing took energy out of the system, but you should ask yourself. State 2, if you pick the table as your reference level, has just kinetic energy, 1/2 mv squared. But if you pick the ground to be your reference level, then you've got mgh plus 1/2 mv squared. Now, I don't know how many of you noticed this, but first, I didn't give m. Doesn't seem to matter. Every term has an m in it, so they all just disappear. But this is the part you should pay attention to. I'm going to have to subtract this from both sides, aren't I? You see that, don't you? Or maybe you don't see that. I'm going to subtract that from both sides. When I do, I will have 10 times 2 minus 10 times 1.5. And that has to equal 1/2 v squared. I can subtract, and I'm doing this on purpose. I could make this a number, but I'm doing this on purpose to show you that this is 10 times 2 minus 1.5, which is 10 times 0.5. So it doesn't matter whether you chose the table to be the reference level or the ground. As long as you are consistent, you are fine. Now you can get the velocity. I don't care about that. I do care about recognizing that there's every reason to believe the next step of this problem is to ask something about the box hitting the ground. And in your notes, you know that your problems on your exam are going to cover multiple topics. There's no reason why we can't have questions on our next test cover multiple topics. So I'm thinking, how far away from the edge of the table did it land? The range. You remember those problems? There is no way to do that. No way to do that but projectile motion. There's no shortcut. That means drawing that little chart, vertical, horizontal, all that garbage. I'm not doing that here. But you understand that this is a obvious next step to our work, right? So you should be considering that kind of review. Moreover, you should realize that if I want to make the thing go further away, hit further away, I probably want to change, how high up on the ramp I start the object. Start it higher up on the ramp, I bet I can make the range get bigger. Those are the kinds of things I think the problems are going to ask of you. But also, I do want to point out something else. I could ask how fast the object's going when it reaches the ground. For that, you could do projectile motion too. But you could also just realize that this is state 3 of the problem. Now, if you choose to make this state 3 of the problem, then the ground has to be your reference level, because that's the lowest point in the problem. But just set that equal to 1/2 mv squared. Notice we didn't need the mass for this problem. But I also want you to know something else. You were never asked for how much energy the object had. Right? Not once were you asked how much energy the object had. Without the mass, you couldn't answer that question. But also, there's something important here that's I'm intentionally kind of dancing around. So let me kind of erase some of the stuff that's in the way just so I can focus, or at least focus you. If I told you the box has a mass of 2 kilograms, something, just so you have a mass, so you can't say, well, I don't know the mass, so I can't answer that question. If I say the box has a mass of 2 kilograms, and I say, how much potential energy does the object have when it's at the top of the ramp? That's an ambiguous question. There is no answer to that question. Does everyone understand? There's no answer. Because just like we showed, with respect to what, Mr. Shelton? With respect to the table? With respect to the floor? With respect to the first floor, because this is on the 10th floor of the building? Asking about how much gravitational potential energy is an ambiguous question. If you are asked it, they have to tell you what the reference level is for that calculation. They have to say, with respect to the ground, or with respect to the table. They need to be clear. So if you're asked for how much gravitational potential energy you have, you need to be provided with a reference level. If it's not provided on the test, either the test was poorly written, possible, or the person is making you assume something. Generally, it's safest to assume that gravitational potential energy will be based on the lowest point attainable by the object. I don't know that the floor is the lowest point attainable, but it makes likely sense if they ask about the floor towards the end of the problem. But if they only ask about the table in the problem, maybe this thing is fragile and they don't want it to hit the floor, and you should only talk about it with respect to the table. I will tell you on my test, but if it's asked on the AP exam or if it's asked on the semester exam, I'm assuming there will be enough context for you to know what the reference level is. Questions? Seems easy so far, right? Maybe? Yeah. I want to know how fast the system is moving just before the hanging box hits the ground. That's what I want to know. How fast is the system moving just before the hanging box hits the ground? Now, if I want to treat this as an energy problem and not a force problem, to treat it as a force problem, we can find the acceleration. We can do net force, get tension, all that stuff, eliminate tension, get the acceleration. We can do that. To do this as an energy problem, though, I need two states of the problem. So this is state number one. Let's see if we can imagine what state number two must look like. State number two, I'm thinking we still have a table. The table hasn't changed. Still have a pulley. Pulley's still there. Still have the floor. Floor hasn't moved out the way. But now the box is just about to hit the ground. So make it just above the ground. And now the box that's on the table has been dragged to the side. Still got those cables in place, still holding the boxes. But now box one is moving, and so is box two. All right, everybody follow along? Two states of the problem, state one, state two. The issue is that there's more than one object, but energies add together. This is a system of connected objects. So let's start with the 3 kilogram box. State one, I release the system. Does it have any elastic potential energy? Is it pressed up against any springs or anything? Does it have any gravitational potential energy? This one's on you guys. Does box 3 ever change its height? No. This is your call. It's ambiguous. It's going to have this amount of potential energy both before and after the box falls. Do you want to include it or do you not want to include it? I'll leave it to you guys. Who would like to include it? Say this box has potential energy. It's about 4 of you. Who doesn't want to include it? It's a lot of you. All right. So, is it moving when it's released from rest? It is moving when it's released from rest or not? You guys need to answer this question. At time equals 0, I release the system. It's not moving. It's at rest. It has no kinetic energy when it's first released. It has no elastic potential energy when it's first released. It's ambiguous if it has gravitational potential energy. On the other hand, is the other box pressed up against a spring? No. Is the other box above the reference levels, above its highest position? I believe so. Is it going to attain a lower position later? And is the object moving when it's released? Box 1 isn't moving. Box 2 isn't moving either. And state number 1, I have M, G, H. I wrote it in there. I don't think I need to, but that's the potential energy that the box has on the top of the table. I'm going to leave it there for just now. The other box, M, G, H, and that's all the energy there is at the first state of the problem. Right there for me, please. Thank you. Appreciate it. So, what?
I just wondering if the 2 kilogram box has a string shorter than the distance to the ground, could it ever pull the 3 kilogram box over the machine?
Yeah. That's why I made it nice and long. My diagram here. But yeah, it's possible to have a situation where this could hit the pulley before the other box hits the ground. It's possible. Yes, sir? I thought you had your hand up. All right, so let's consider state 2. I'm taking too long on this. State 2 has box 3. Does box 3 have gravitational potential energy? It does if you think it's above the ground. I wrote it here, so I better write it over here because it's still the same height. This is just to prove that you're going to have it on both sides. It'll cancel out. But I'm putting it in there to ensure you that those of you who don't fully understand why you have to or not have to include it, well, it's the same on both. Its potential energy didn't change. This is about change. The energy is coming from somewhere. The box at the table didn't lose any potential energy that could cause the system to speed up. The box that was hanging, though, did. But don't forget, the box on the table now also has kinetic energy. So they both acquire kinetic energy. Both the box that's about to hit the ground and the box that's on the table both acquire kinetic energy. So in state 2, they're both moving. A lot of people want to say, but box 2 hit the ground. Isn't it stopped? It's not what the question asked. It asked, how fast was the box going when it hit the ground? When it hit the ground, it was moving. The ground stops it. But that's not what the question asked. It asked, how fast was it going when it hit the ground? So we assume it's moving when it hits the ground. This is the answer. I don't want to work out the problem. You work it out, okay? You can do this. You can cancel things out and you can add and subtract. We gotta pick up the pace here. My intention is to pick up the pace right with this question. Because all these questions so far have left out something. What kind of energy have we not had yet? Well, friction, sure, but that's not one of the things I'm talking about. So we should have something with a spring involved. That way we've covered all of our bases here. There's lots of spring questions, bow and arrow questions, stuff like that. They're all the same kind of thing. So I've got a spring launch little roller coaster thing for my car. And let's say that this is a 1.5 meters high. And this side is just, say, based on the way I drew it, we'll say that it's like 0.8 meters high. Spring has a spring constant of 1,200 newtons per meter. Spring constants should be big numbers. So expect them to be larger numbers in your problem. Also, spring constant is the only thing that has units of newtons per meter. Kind of easy to pick that one out. The car has a mass of 0.75. Now let's make it smaller. 0.25 kilograms. Here's the question. How far back would you have to pull the car so that when it's released, it makes it to the top of the first hill? How far back do you have to pull the car against the spring so that when it's released, it makes it to the top of the first hill? Now, we're not going to have time to go through this problem, but you should probably recognize that this is the reference level and that to just make it to the top of the first hill, we're talking about the amount of energy to just get it there. All right. I did this problem in first period. I'm going to post it. You should review it. It's the last 3 minutes of the first period video.